Welcome to a new test and teardown video. This time it's a Philips HF Generator PM5324. It handles 100 kHz to 110 MHz. It is from about 1973. So it contains transistors and ICs and all that. I went to the Radio Museum webpage, and there it says 26 transistors and ICs and stuff like that. So that's pretty cool. And I got two of them. Ta-ta-da! And they are in a little bit different shape. For example, this one got a really nasty looking scale. But other than that, I've been around touching all the knobs and potentiometers here. Ooh, this one goes a little bit tight. Yeah. So I got these from a friend, and he was asking, is it possible to make at least one of them working? And then, yeah, well, that is what I will try and do. Let's see if I can make one of them work. And I already found a little Philips repaired service in 1975. This one went to service the first time. I'm not gonna go and ping pong back and forward in this video. I'm just gonna look at one of them, and then I think I will just go and play with that one. If there's something here that's not working, I will just go and try and poke it from the other one maybe, because I think this one is the most beautiful one. I'm quite happy to see this model uses a modern mains connector, so that is pretty good. And you can from the outside see the selected mains voltage, so that is also really good. And here is the plate. It says this is a -01 model. I think they come in different options with some things like that, but we'll see about that. So I should expect about 10 watts of power usage. I always check this, super important. When you power up old stuff, always monitor power usage. And then if it's, double that, you have to abort immediately. And we are now inside this fantastic Philips, but it wasn't without a little bit of crying and a little bit of yelling. So let me tell you a little story about the mechanical design. So first of all, the sides, they're pretty easy. The handle screw, this one handle screw, if you take this out, then you should pop out the side, and they lock on the other end like that, easy peasy. Of course, this one is a little bit, I don't know, it was maybe dropped on the floor or something. So that means if you put it carefully in here in one side, it's not gonna fit. It's yeah, not super duper good. But there's another thing that is driving everybody nuts, and that is, so this is the outside. Let's look at the inside. And it is this little thingy up here, that one. It is not really in use in this product for other purposes than driving everybody nuts. And of course, they're using the same side panels for all sorts of different designs. And this is why you have all those different holes and thingies, and those are not in use, and so on, right? So this is the top plate. Let's just pretend it is mounted. Maybe I should show you this first. Look at those little metal lockies. So when you go here into the front and then push this in, clickety clackety, lockety here at the front. Alrighty then. So when you want to pull this out, you just go backwards. But you can probably see it down there. This little nasty thingy hits something, and that something is this piece of plastic right there. And this prevents you from pulling anything out. You get completely locked up by this here. It goes click, and then There is no way in heaven. See? Click. And there is no gap between this and the front where those lockies they go in. So that drove me absolutely crazy. What I really suggest to do is to cut a few millimeters off this, like that, and then you will have a happy life again if you ever need to go into one of those Philips units. What the? Yeah, anyway, now I'm happy again. And yeah, I can show the inner workings of this fantastic generator. What you get here is about 50% air. Underneath here is just half of it is air, and again on top also half of it is air. The mains transformer is of course furthest away from all the signal stuff, and especially this capacitor that sets all the frequencies. And we flip it a little bit around here. All those holes and those numbers, that will be trimmers and adjustments and all the goody things down here for all the different frequency bands, frequency ranges and adjustments. And we need to open this to have a little look what is going on, of course. Up here we got the power supply, and I've inspected the capacitors. They look good. Rectifier bridge looks good. And yeah, I feel that we can power this up, and we need to of course have a little look in here first, but other than that, yeah, oops, also need to glue that one, also need to glue the front, so I will do that. All the switches feels good, and the goody click here, so all that is fine. It's the same here at the back, where there's a nice metal plate that covers all the high frequency stuff. And it seems like it's quite easy to remove that one to gain access. They even made a little groove here so the wire is not in the way, or is not preventing us from taking this plate away. And that will be the bottom of the power supply and some sweep stuff. This one here is going to that, I guess. We'll have to see. Yes, I actually found one tiny little thing to complain about. The mains on-off goes a little bit tight. I feel I need to give this a little drop of cleaning. It's so funny to see that it's not all cool design ideas, I understand. So here at the side, there's a little lid you can remove, and then what do you know? You can see the capacitor, but there isn't any trimmable or any accessible parts. I mean, why would you have this hole? What is it good for? Well, that is a one big mystery. I better put it back. I would open the top and the bottom and then do whatever you need. You can't do anything through this hole. Let's try and look a little bit inside. I have, of course, removed this metal shield, and now we can see all the different trimmers and adjustments. There are quite a lot of them. And there's another one. Here's a little crystal oscillator. I think that is 10 megahertz. And I think the ICs are from 1972. It's on that one. And over here, another 72 and 72. So maybe my unit is from 1972. Here on the back side of the meter, or the scale, this will be, of course, the different LED indicators. So for 1972, look at that, LEDs on the back side of that little circuit board. That, of course, they indicate the different frequency bands, and the scale is illuminated by 3 bulbs. And there's also a little bulb inside that meter. And another funny thing is the little rubber thing here. See, this is not correctly mounted. It was supposed to go behind this piece of metal here, like it is on the other side. So that means my meter See? It's flippity floppity, so I'll probably add a little drop of contact glue here or something, so it's gonna be nice and fine. Now we got some fancy ICs as well. GAA 310 7490, that's 10 and 10 counters. And there was also a metal shield here at the back of the oscillator part. We got a little bit of modifications, see, but this is professionally done. Maybe that will be some repairs, because the rest of the board, the solder quality looks absolutely fine. So that's probably some a little bit of homebrew modifications. This is not just a normal potentiometer, it's actually an attenuator in two, I don't know if it's easy to see, but we got two different parts of a potentiometer that's connected together. So it's an attenuator with the correct input and output impedances. So after my visual inspection, I feel I am ready to test this thing. So that will be my first power on. So first we put on mains, and then we verify it's not using any kind of power, and then power on, and it's using 10 watts, and that is absolutely normal. I have selected 123 megahertz, and then it neatly shows with a nice little red LED. Look at that. So that is the top scale. So if that is the top scale, okay, what if we dial it into 2? So here is exactly 2. All right, let's look at the scope. And what is that? Here on the top is the frequency, right there. And that is pretty close to 2 megahertz. Ha ha! What kind of luck is that? And it's so beautiful with the light and all that. I'm super happy about that. Let's try and see if all those 6 LEDs they work, because they are very old. Ah, then it goes back to this other scale. Cool. I mean, all the LEDs work. I really want to try this wobbler, because there's a built-in sweep system here. And I think what they wanted to show here with the 3 buttons to the right, that is, of course, that you can only use this wobbler, this sweeper, in those 3 frequency bands. And that is, of course, because it's made using another oscillator, and they're beating and mixing those 2 oscillators together to generate the output frequency, and that is, of course, how it is. So let's try and play with that. So in wobble mode, or this sweep system, I have selected 10 to 11 megahertz, and then you can, of course, dial in the frequency to whatever frequency it is. The idea is, you can see it's beating here. Ooh. And this is because there's another oscillator that is beating with. And also, this is a sampling oscilloscope, and so there will be some beating with the sampling. So what is happening here, look. Now I'm changing the sweep, and then it's interfering with the sample of my oscilloscope. And this we're generating all sorts of funny lower frequencies, like you can see here, where the output actually sweeps different frequencies, and my scope also takes samples. with an analog oscilloscope, you wouldn't see this at all. It should just go super smooth. At least that is what I was hoping for. If we turn off this wobble like that, now we have a fixed frequency of 10 megahertz, and then I can just dial the frequency, and then you see. So here's an interference with the sample rate of the oscilloscope. Isn't that cool? And if I go faster, 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 here you go. Now you see the 10 megahertz, the true output. And if I now go into wobble, you don't see any change. I mean, you see it like this. It has a frequency change. And this weak pulse you see up here, that is the start of the sweep. There's a little bit of a DC plop in the amplifiers, and that is not a wanted effect, but yeah, there's a nice sweeper here. There is another feature here called calibration. So if you hit cal, then we have light in the meter, and then there is a readout of this meter at every 100 kilohertz. And this way you can monitor, for example, here is 10.7, and then you have a meter readout like that. And the idea is you hit this maximum, and then you hold the big scale, and then you turn the small one. And this way you move the indicator until it hits 10.7. As you can see here at the moment, it is a little bit to the right. So let's try and see what we can do. Okay, so I put it here, and then I dial it. That is how it is. It is actually only moving. Maybe there's a mechanical thing, but it's only moving a tiny little bit. That is weird. I was expecting it to be able to move more. Maybe I'm doing something wrong. Maybe I should... I don't want to break it. It is responding here. But I need this to be 10.7, and it is 10.66. It's not like it's a big, big problem. But anyway, just a little fun. How can we play with this, and what can we do with this thing? So I'm trying to show here is a sweep, and the sweep output is driving the yellow channel. So you can of course use this to sweep on the scope and whatnot, right? So, and the RF output is about 10.7 megahertz, and I drive this via a little amplifier, and this amplified signal, because this is only a really low signal, all right? So I take it via a little crystal and a little rectifier diode, a resistor, and a capacitor to make it into this. So the fun thing is, this point here is of course the 10.7 megahertz, right? And we can poke around with the frequency, and then see what happens when we sweep the right frequency. And we can also play a little bit with the sweep. How much? Ooh, if you're going super narrow or super wide. We can also play with the amplitude. See what happens. See what happens when I overdrive. This is obviously the amplifier. And then I go a little bit down, and there you have it, nice and fine. And if I have too little signal, then I'm not able to see the rectified signal. That is of course a problem. So here you go, totally overdriving, and back again. So I think that is more or less what I wanted to show you, a little practical example user experiment. But yeah, I think still this is a very useful instrument. It could be used for a lot of cool things. So thank you very much for watching, and I hope to see you soon again. Bye bye.